So here we go with lesson number 14. You guys are all enjoying the gift of a new packet, an even bigger packet than the first packet, right? This is, right? Like Christmas and Hanukkah all rolled into one right here.
This is actually like the last packet. There we go.
Yeah. All right. Everybody up here. Everybody up here. Okay. As Matt just asked, yes, this is the last packet that I will give you. This is going to carry us through the end of the semester all the way through to the final exam. Only 2 packets this semester. This guy's a little bit longer because we're not quite at the halfway point of the semester when I'm giving it to you. All right? So, looking ahead, we are starting right here, class number 14, which is about the Pythagorean Theorem and something else. What else does it say? Laws of exponents. Brand new topic, brand new flavor, brand new everything. These problems will look nothing at all like all the systems of equations we've been doing the last couple of weeks. Just brand new. To be clear, again, this is not on the coming test. The test is in 1 week. We just finished the material that's going to be on the test. This will be on the next quest, which we'll talk about later on, but this is not on the test. Irene.
When is the test?
The test is on October 15th, 1 week from today. You see it on the left there? Test number 1 covers everything so far. Stopping right now, even though we're moving on. Other questions? We have, okay, so the calendar, I did what I could. I'm asking a lot of this 1-page document. The 2 columns on the left are independent of all the stuff on the right. There's this like light gray bar that I'm trying to do my best to separate. Left-hand side just tells us what today's date is and what we are covering. The right-hand side is more details and when like homework assignments are due. So we are covering class 14 right now, which is way down here, and this homework is due October 20. But it's not on the test, which is happening earlier. Next Thursday we have 14 and 15, and then on the 15th, I think I said Thursday. On Tuesday we cover 14 and 15. No, the dates of the quests are in this second column right here. Next one is the 29th. All right, so here we go. So we gave you 2 handouts. One of them is this massive packet, and then the other one is a 1-page handout. So make sure that doesn't get lost in the shuffle. That 1-page handout you are going to use on quests and tests, okay, and the final exam. So this will help us. We're going to talk about powers soon enough. All right, here we go. I realize now I should have hole punched those. Sorry about that. Okay. Lesson 14. In this lesson, we solve story opportunities, word problems, with the Pythagorean theorem, and we begin our exploration of exponents by using certain rules to simplify expressions containing exponents. So 2 things. Pythagorean theorem is kind of a one-and-done topic we'll cover now and then really not talk about anymore. And then exponents we're going to talk about quite a bit over the coming classes. So we'll start with Pythagorean theorem. You guys all know this theorem, right? It's the most famous theorem in all of mathematics. It has to do with right triangles. If you have a right triangle where the legs are AB and the hypotenuse is C, then we get that most famous of equations, a squared plus b squared equals c squared. Got to make sure you put the hypotenuse by itself. You can swap a and b, but hypotenuse has to be on its own in the equation. So let's try number 2 to make sure we're good with that theorem. You're shopping for a home entertainment center and find one at a good price. The space for the TV in the entertainment center measures 17 inches by 21 inches. You are wondering if your 27-inch TV will fit in the space. Will it? Note that TVs are advertised by the length of the diagonal. So when we say the TV is 27 inches, we are talking corner to opposite corner. All right? Anybody know why people advertise TVs by the diagonal as opposed to the length or the width? It's bigger. It makes it seem bigger anyway. The diagonal is the absolute biggest thing you could possibly measure in a rectangle, right? It's pure marketing. When we say the TV is 27 inches, you might have visions of 27 inches across or 27 inches on the side. Neither of those is going to be close to 27 inches. 27 is the longest thing you could possibly find. In some sense, it's artificial, but it's marketing. So let's draw our TV screen here. not our TV screen. Let's draw our entertainment center space. So we're going to put a 17 there and a 21 there. And we're trying to decide if a 27 will fit on the diagonal. So it seems reasonable to draw that diagonal. I'm not going to put 27. I'm just going to leave that as an unknown. If I'm going to use a letter A or B or C for the length of that green, only one of them is the right choice. Which one is the diagonal? It's C, right? You guys know the word hypotenuse from a previous math class. We know that the hypotenuse, this longest side, is always the one opposite the right angle. So got to call that guy C. And now we're going to use this most famous of equations. A squared plus B squared equals C squared. 17 squared plus 21 squared equals C squared. We're just calling it C. Okay, 17 squared. You guys are reaching for your calculators. Put them away. Let's use our new table. Right up here. You could also use the perfect squares. Are they behind me? Perfect squares are behind me, but 21 is not. Smarty. Yeah, so the perfect squares are yellow. This guy has even more than I have on my wall. So make sure you can find 17 squared on your perfect power sheet. Everybody see it? Perfect squares are the second column. We go to 17. What do we find? 289. That's what goes right here. Plus 21 squared is 441. Everybody see that in the charts? That is equal to C squared. We'll add these guys up. 3, is that 730? It is. We're going to solve this guy right now for C. Everybody good so far? C squared equals 730. We will talk about this soon enough, but what's the opposite of squaring something? Square rooting. So we are going to square root that 730. This is a symbol we will define soon enough, but you've already seen it, so I'm just going to use it. Square root of 730 on the calculator, somebody? Can you give me some change? 02? So 27.02 inches. That is the space along the diagonal of our entertainment center. So will our 27-inch TV fit? No? That is the space. 27.02 inches available.
And we need 27.
And the TV is 27, so we'll just barely squeeze in there. We better hope there's no like frame around this TV. Okay? All right. I'm going to have to change this problem soon because TVs, I think, are going by the wayside. All right. That's Pythagorean Theorem. I'm done talking about Pythagorean Theorem. Number 3, exponents. Like I said, we're going to spend a lot of time on exponents. Fair warning at the beginning of our many lessons in a row on exponents. Exponents are one of the hardest topics of the semester. I'm not saying that to scare you. I'm just saying that to let you know that you should expect to work, that these problems are going to be challenging. They might start off kind of easy, but very quickly they're going to become difficult. Number 3, let's shift gears and talk about exponents. Many of the rules for working with exponents follow naturally from the definition of an exponent. Here are some examples. Okay, 7 squared. We all know that means 7 times 7. I'm not super interested in the fact that it's 49, just that 7 squared means 7 times 7. 5 to the 4th really means 5 times 5 times 5 times 5. Yeah? Easy peasy. 2 to the 8th means you multiply 2 times 2 times 2, 8 of them all together. Good? Everybody has seen exponents before. Okay, just some vocabulary. If you see x to the n, we call x the base of that thing, and n is the exponent of that thing. So for 2 to the 8th, is that 2 the exponent of the base? That is the base. And then that 8 right up there is the exponent. All right? Okay, there are 5 laws of exponents here. We are going to see more of them, but here are our first 5. Some of these you are going to start to develop shortcuts for. But in the beginning here, I want to make sure our intuition agrees with the formulas. So let's take a look at this guy right here. 3 to the 5th times 3 squared. There are 2 very reasonable answers for what that might equal. Maybe it's equal to 3 to the 10th. What did I do with the powers? Multiply them. I see a multiplication symbol, 3 to the 5th times 3 squared. So 5 times 2, 3 to the 10th. 3 to the 7th is another reasonable answer. What did I do to the powers? I added them to get 7, right? Now, maybe it's one of those things. Maybe it's something completely different. The point here, I don't want you just memorizing. I need us to have some context because there's always multiple things that seem reasonable with exponents. And there's only one right answer for these problems. So we got to make sure we're clear on these basic rules before we move on and just go to memorization. So 3 to the 5th really means 3 times 3 times 3 times 3 times 3. Just 5 of them written out. 3 squared really means 3 times 3. And if you saw this and you said, oh, I'm going to group all those 3's together, how many do you have? You have 7. And so what are we doing with those 5 and the 2 to get our answer, which is 3 to the 7? We're adding them. It's a surprise the first time you see it. This is a multiplication problem. But for some reason, the right thing to do with those powers is add. What's the reason? The reason is listed out there. You're just collecting all of these 3's. Okay? This is our first example where a perfectly reasonable answer, 3 to the 10th, is just not right. So I'm not about memorizing at this point. I want us to develop this intuition. Same idea down below. The next one we'll talk about is 3 to the 5th over 3 squared. Perfectly reasonable to think that we should maybe take the 5 and 2 and divide them. After all, this is a division problem. Turns out that isn't the right thing to do. 3 to the 5th upstairs, just list 5 of them. 3 squared, list 2 of them downstairs. Then we cancel. 3 and 3 and 3 and 3. How many 3's are left? 3 of them. Why are there 3 of them left over thinking about the original 5 and 2? Because we should subtract those guys, right? The 2 cancel, and you're left with 3 at the end of the day. So 3 to the 5 minus 2, and that's our next rule. Moving on, 3 to the 5th to the 2nd. 3 to the 5th squared. Let's list this guy out. 3 to the 5th squared really means 3 to the 5th times 3 to the 5th. Yes? And 3 to the 5th, I've just listed 5 of them. And then the other 3 to the 5th, I've listed 5 more of them. How many 3's do we have? 10. And is there a shortcut that you can do with the original 5 and 2 to get 10? We can multiply them. So in cases like this, 3 to the 5th, the whole thing squared, multiplying those exponents is right. But multiplying we saw was not the right thing to do up there. And so already we're seeing 2 different problems where it feels like multiplication might be the right thing to do, and it is in one, but not in the other. And this is part of why, this is essentially why exponents are hard, is because there's always reasonable things that aren't right. Okay, last 2 properties. 3 to the 4th, the whole thing cubed. Okay, so that means 3 to 3, I said 3 to the 4th. I meant 3 times 4, the whole thing cubed. So 3 times 4, 3 times 4, 3 times 4, cubed, yes? Now we're gonna just shuffle together the 3's in the front and the 4's at the end. So 3, 3, 3, 4, 4, 4, that's just regrouping. How many 3's do we have? And how many 4's do we have? 3. And so apparently, when you have 3 times 4 cubed, you can, in some sense, bring that power in, and I'm going to use the word distribute. 3 to the 3, 4 to the 3. It feels like distributing to me. Distributing is not the right word. Distributing is a very special, it's clearly defined. 5 times 6 plus 2. This is distributing. That's not what we have. It looks like distributing. But anyway, this is why kind of distributing is allowed in cases like that. And the last one is the same idea, but instead of multiplying in the parentheses, we're going to divide. You list it all out, you see that again, the exponent, quote unquote, distributes to the top and the bottom. We end up with 3 cubed over 4 cubed, okay? All right, so I think that is good. So as you get to problems in the activity today and in the homework and the same thing for the coming lessons, if you're ever not 100% sure of what rule you are allowed to apply, you just make up numbers like these ones that we just looked at. Make up something small. You're going to do problems with X's and Y's and Z's. Change them to numbers. Do something that you can tie into and say, oh, I understand why in this first example, addition is the right thing to do. Or in the second example, it's a subtraction. So if you're not 100%, go to numbers, figure out what the rule must be, and then do it more generally with your variables. Okay, two more things here on the next page, number 5. It's important we can handle negatives and exponents together. We're going to try these without a calculator. First one, -4 in parentheses squared. That means -4 times -4. Everyone agree that's what squaring that thing means? And what is that equal to? 16. That's the right answer. The next box is a -4 squared. And I know some people in this room are looking at that and thinking it's the same problem and it's the same answer, 16. But it is not. Because that squared is not strong enough to affect that negative sign in the front. Exponents just have a smaller reach than a lot of us give them credit for. If you think about the order of operations, PEMDAS, we've seen that before. Parentheses are first. I don't see any in this example. Exponents come next, and after all the exponents are done, we deal with the multiplication, and I'm going to rewrite this so that you see that there is a multiplication in this problem. Doesn't look like it, but there's one there. It's implied. -1 times 4 squared. That's what a negative sign means, right? It means -1 times. We don't write it, but that's what it means. So in terms of the order of operations, which one do we have to handle first? The times, the multiplication, or the exponent? We got to do the exponent first, which means that -1 times is just hanging out waiting for this exponent to finish. So I'm going to write -1 times, and now we do the exponent. 4 squared is 16. And so what's the answer to this? -16. Do not give exponents more reach than they have. Exponents are weak. They only affect what they are explicitly touching. In this case, that exponent is only touching the 4. It is not strong enough to reach the negative. How come in the first example, the exponent reached the negative? Because of the parentheses, right? In order to give the exponent some artificial power, you got to give parentheses. That's the only way they can get stronger. Okay, next example. What are we doing here? This guy. Okay, that negative sign I'm going to copy here. -4 squared, we've seen it already. What is that? That's +16. And so our answer is just plain -16. Very common mistake on a problem like this is for people to say, oh, 2 negatives make a positive, right? You guys have done that many times. Like if I gave you 3 minus -7, what would you change it to? 3 plus 7, right? Everybody would do that. What's the difference? What's not a part of? Yeah, this negative sign in the parentheses is not available to us because it is being squared. It's not really a negative. It's going to become positive, right? So you don't get to merge those 2 negative signs together. This exponent, that squared, takes priority and says, hey, before you do anything, I'm going to figure out what's going on with this -4. I'm going to square it, and that's going to change the number. Then you can deal with that negative in the front. Lots of ways to go wrong here. Okay, number 6, last one in the demo, and then you'll play around with these for just a couple of minutes before we call it a day. In addition to the 5 laws of exponents, those are the ones on the previous page, there are some other properties of exponents. Here's one of them. A to the 0 is 1 for any number other than A equals 0. In plain English, any non-zero number raised to the 0 power is 1. Or in even more plain English, but a slight lie, anything to the 0 is 1. Anything to the 0 is 1. It's kind of a surprise for a lot of students. But right over here, if I say 4 to the 0, I know that a lot of people think 0, like if you don't have any 4s, then you have nothing. But what I'm telling you is that any number to the 0 is 1. So what's the answer to this?
1.
Is 1. Type it on the calculator. Just make sure your calculator knows that any number to the 0 is 1. If you have one. If you don't have one, it's okay. But if you type in 4 raised to the 0 power, what do we get? On the calculator, people are confirming it's 1. Yep. So I'll talk about why we defined 4 to the 0 to be 1 next class. So right now I'm just saying it's something that we have to do, and just believe me for a second. I'll explain it next class. But any number to the 0 is 1 is something you're going to take away here. So that is equal to 1. 5x to the 4th over y to the 17th, all raised to the 0 is 1. Easiest problem on the next quest. I'm going to give you some ridiculous stuff, but then I'm going to raise it to the 0, and you're going to say, oh, he's just playing a prank on me. I don't have to pay any attention to what's in there because anything to the 0 is 1. How about this next one? Negative 3r to the 0 is 1. Piece of cake. Everything is 1. Negative 3r to the 0, same problem. Negative 3. This one?
No, the 0 exponent only affects the r. It's not far out until negative 3.
Everybody buy what Lennon just said? The 0 only reaches the r. So the negative 3 is hanging out waiting. There is a 1 in this problem, but it's not the final answer. It's the r to the 0. Say again, Catherine? Why? Yes. Negative 3 times 1 is exactly what this is saying, and that is equal to negative 3. Okay, we have 7 minutes. I know we are tired, but we are going to push through for 7 minutes. See if you can get the table on the next page filled in, or at least as much as possible in the next 7 minutes.